Hello and welcome to Module 1 of our course on soil mechanics. In this module, we are going to lay the foundation, quite literally, for everything else we'll study about soil behavior, classification, and engineering use. Think of this session as the geological and physical DNA of soil, where it comes from, what it's made of, and how its internal structure controls its performance under load, water flow, and environmental conditions. Now, soil mechanics isn't just a collection of dry numbers and definitions. If you've ever wondered why some buildings stand for centuries while others tilt and crack within a decade, or why roads fail quickly in certain areas but last longer in others, the answers are often buried, again, quite literally, in the soil. Let's start with how soils form, because the story of soil begins long before a construction project is even conceived. 1. Formation of soils. Soils are not random collections of dirt. They are the weathered and altered product of rock materials, the result of geological, chemical, and biological processes working over thousands, even millions of years. We can broadly divide the process into two main categories. Physical weathering, where rocks break down mechanically without changing their chemical composition. Chemical weathering, where rocks are altered at the molecular level, producing new minerals and fine particles. 1.1 Physical weathering. Physical weathering is the geological equivalent of a demolition crew using only hammers, no chemical reactions, just physical force. It occurs due to temperature changes. Rocks expand when heated and contract when cooled. In regions with large day-night temperature swings, this expansion-contraction cycle weakens the rock over time, causing cracking and fragmentation. Frost action. In cold climates, water enters rock pores and cracks. When this water freezes, it expands, exerting pressure on the rock and breaking it apart. Abrasion. Wind, water, ice, or moving sediments can physically grind down rock surfaces, producing particles that may become soil. Biological activity. Roots growing into cracks can exert enough pressure to split rocks apart. Burrowing animals also contribute to the mechanical breakdown. The result of physical weathering is rock fragments that range from boulders to sand-sized grains, with little alteration in mineral composition. 1.2 Chemical weathering. Chemical weathering, on the other hand, is like sending the rock to a chemical lab where its minerals are transformed into new compounds. The main drivers include hydrolysis. Water reacts with minerals, forming new clay minerals and soluble salts. Oxidation, a reaction of oxygen with minerals, especially iron-bearing ones, producing oxides and hydroxides that change the rock's color and strength. Carbonation, carbon dioxide in water forms carbonic acid, which dissolves certain minerals like calcium carbonate. Solution, the direct dissolution of minerals into water without new mineral formation, common in limestone regions. Chemical weathering tends to produce finer particles, including clay minerals, and significantly changes the soil's engineering behavior, especially its plasticity, strength, and permeability. 1.3 Residual versus transported soils. From the mode of formation, soils are classified into two broad types. Residual soils, these remain in place over the parent rock after weathering. They typically have properties closely related to the original rock type, though modified by weathering processes. Example, tropical laterite soils rich in iron and aluminum oxides, formed in situ. Transported soils, these have been moved from their place of origin by agents like water, wind, ice, or gravity. Transport modifies their properties. Subtypes include alluvial soils, deposited by rivers and streams. Aeolian soils, transported by wind, such as loess and dune sands. Glacial soils, moved and deposited by glaciers. Colluvial soils, moved downslope by gravity, often forming talus deposits at the base of slopes. Understanding whether a soil is residual or transported is crucial, because it directly affects its engineering properties, such as drainage capacity, strength, and uniformity. 2. Soil-water relationships. Water is the invisible puppet master in soil behavior. You can have the same soil, but with different water contents. It can act like a rock, like quicksand, or like plasticine clay. Soil-water relationships describe how water exists in and interacts with soil pores, influencing strength, compressibility, and permeability. In engineering, we typically think of three phases in soil. Solid phase, mineral particles. Liquid phase, water. gas phase, usually air. The relative proportions of these phases determine key soil properties. 2.1 Moisture forms in soil. Water in soil can exist in different forms. Gravitational water drains freely due to gravity, unavailable to plants but important for drainage analysis. Capillary water, held in small pores, available to plants and important in soil suction studies. Hygroscopic water, tightly bound to soil particles, unavailable for plant use, negligible for flow but important in soil-mineral interaction studies. From an engineering standpoint, capillary water is particularly important in fine-grained soils, as it controls shrink, swell behavior and apparent cohesion. 3. Void ratio. The void ratio is the ratio of the volume of voids in a soil to the volume of its solids. This tells us how much empty space exists relative to solid material. Why is this important? Because the void ratio directly influences compressibility, permeability, and strength. A soil with a high void ratio tends to be more compressible and less stable under load. A low void ratio usually indicates a denser, stronger soil. 4. Porosity. Porosity is the percentage of the total soil volume occupied by voids. It's closely related to the void ratio, but expressed as a fraction of the total volume rather than the solids. High porosity in coarse soils like gravel may still allow high strength, because the particle interlock is strong. In fine-grained soils, high porosity often correlates with high compressibility and low strength. 5. Specific gravity. Specific gravity in soil mechanics refers to the ratio of the density of soil solids to the density of water. This value is a clue to the mineral composition of the soil and is critical in phase relationship calculations. For example, quartz-based sands tend to have a specific gravity around 2.65. Organic soils may have much lower values. Understanding specific gravity helps in computing void ratio, degree of saturation, and other vital parameters. 6. Interrelationships of soil properties. These parameters, void ratio, porosity, specific gravity, and water content, don't exist in isolation. In design and analysis, we often calculate one from another. For example, given the specific gravity and water content, we can deduce degree of saturation and dry density. The interrelationship also helps engineers predict how soil will behave during compaction, loading, and saturation, or critical for foundations, embankments, and earthworks. 7. Engineering significance. So why have we spent so much time on these basic properties? Because they underpin every geotechnical decision you make. Whether you're designing a dam core, planning an excavation, assessing slope stability, or simply deciding if a site is buildable. Understanding the formation, structure, and water relationships of the soil will tell you more than almost any other single factor. In Module 2, we'll go deeper into classification systems, flow behavior, and the laboratory tests that allow us to measure these properties in practice. This is where theory meets applied engineering.